Hello everyone. Today, I'm excited to present our winning solution to the ScanNet++ Novel View Synthesis Challenge, on behalf of our team. The title of our work is Distilling Radiance Fields with Robust Point-Based Graphics. This project is the result of close collaboration among the listed authors, and we are honored to have received the top ranking in this competitive track. Let's begin by looking at the core challenge of the task. The benchmark is built on the ScanNet++ dataset, which comprises over 1,000 indoor scenes, including 50 high-quality benchmarking scenes used for evaluation. These scenes include high-resolution DSLR images, and they represent a wide variety of environments ranging from apartments and classrooms to offices and laboratories. What makes this challenge particularly demanding is the presence of glossy and reflective materials that are difficult to model, especially for view-dependent effects in novel view synthesis. As shown in the figure, another key issue is the significant difference between the test poses and the training trajectories, not just in terms of position but also orientation. This means that the test views are not merely held out frames sampled from the same camera trajectory, like in traditional NERF setups. Instead, they are entirely independent and unseen viewpoints. This introduces strong generalization demands and pushes any novel view synthesis method to go far beyond interpolation into true extrapolation. To address this, we compare three mainstream rendering paradigms and analyze their strengths and limitations. First, Gaussian splatting offers fast and sharp rendering results, especially for training views. However, it tends to overfit and exhibits artifacts when tested on novel views. Second, NRF-based methods are continuous and more robust to viewpoint changes but often produce blurry results and struggle with complex, view-dependent appearances. Third, point-based rendering, such as RPBG, aims to bridge these gaps by combining explicit point structures with implicit networks, offering a more balanced trade-off between robustness and fidelity. Building upon this, our main idea is to further unify point-based graphics with neural rendering. We leverage the explicit geometry to preserve structural integrity and use neural fields to model view-dependent radiance. We call our final method Distilling Radiance Fields with Robust Point-Based Graphics. This approach fuses the strengths of explicit point-based geometry and implicit radiance modeling. It provides not only improved robustness to large viewpoint shifts but also consistent, high-quality renderings across diverse scene types. Our pipeline consists of four key components. First, we apply off-the-shelf multi-view stereo algorithms to reconstruct accurate 3D point clouds for each scene. Next, we use a point-based neural renderer that projects point features into the 2D image plane and reconstructs images through a learned decoder. We also design a self-supervised artifact removal module that identifies high-confidence regions in the generated images and filters out noisy outputs. Finally, we perform ZipNoRF distillation, where high-confidence outputs from the point-based stage are used to supervise a NERF, enhancing view consistency and generalization. This process is conducted in a self-supervised scene-by-scene manner. On the ScanNet++ benchmark, our method achieves top performance across all three standard metrics, PSNR, SSAM, and LPIPS. This clearly demonstrates our approach's effectiveness in synthesizing novel views, even when the test poses are far from the training distribution. It also outperforms both classic and recent state-of-the-art approaches in this highly challenging setting. Compared to the RPBG baseline, our approach produces fewer artifacts in sparsely sampled regions, largely due to our distillation strategy which encourages multi-view consistency. When compared with ZipNoRF, our method better captures view-dependent details, such as specular highlights and lighting variations, thanks to the fusion of explicit and implicit representations. In the PSNR results shown here, RPBG achieves 18.42, ZipNoRF scores 19.79, while our method reaches 20.04, the highest of all. This validates our method's superior generalization and photorealistic rendering capabilities. Here are several visual examples of our rendered outputs. Our method successfully handles challenging scenes with complex lighting and texture, and is capable of synthesizing views that are significantly different from the training trajectory. Even in difficult scenarios involving occlusion, specularity, or scene diversity, our results remain stable and visually plausible. Thank you all for your attention. We're excited about the future of combining explicit and implicit representations in neural rendering. For more details about our method, or if you're interested in discussing the implementation or training procedures, please feel free to reach out to us by email. We'd be happy to connect and share more.